Good morning, Dr. Surendar Singh. You are on mute. Yeah. Good morning. Good morning, Dr. Surendar Singh.
Sorry, I'm late.
We
Actually,
know. We know.
yeah, the net stopped working
Yeah,
suddenly.
I informed all the participants. It's not no issues. You can relax yourself and start, sir. No issues.
Okay.
You're audible now. Uh,
Yeah.
Shanmuga, just give a brief introduction about sir so that we can start.
Yeah, yes, sir. Good morning to one and all participants who are coming for the day 3 session. So, day 3 session of AICTE for that STTP program. I heartily welcome you all. And I also welcome our guest lecturer, Dr. Surendar Singh. And I would like to give a brief introduction about you, sir. Dr. Surendar Singh is an assistant professor in the Department of Civil Engineering, Civilization of Transportation Engineering, Indian Institute of Technology, Madras, Chennai. He completed his PhD at Indian Institute of Technology, Roorkee, India in 2018, where he worked extensively on the vulnerization of reclaimed asphalt pavement (RAP) organic waste from bituminous asphalt pavements for cement concrete pavement applications. Declaration on RAP for sustainable concrete pavements has uh, sorry has received a prestigious Indian National Academy of Engineering Innovative Project National Award in 2019. Surendra obtained his bachelor's in civil engineering from State Government College, DC or UST, Rohtak, India in 2013, and went to pursue his MTech in Transportation Engineering at the National Institute of Technology, Kurukshetra, India 2013 to 2015. The dissertation topic was related to the design of cement concrete pavements, the findings of which also earned the prestigious Indian Road Congress IRC Bihar PWD National Medal in 2017. Presently, Surendra is working on different aspects of concrete pavements such as valorization of recycled materials, design and monitoring of concrete pavements, roller compacted concrete, and rural roads. In total, he has published more than 30 dedicated scientific articles on sustainable cement concrete mix in various international science citation indexed journals. Besides, Surender is an executive board member in Indian Concrete Institute, ICI, Chennai, and is currently serving as topic editor for the International Journal of Frontiers in the Built Environment. Thank you, sir. Good morning, sir.
Thank you, Priya. Thank you. Can I share my screen?
Yeah. No, sir, your screen is not visible, sir.
Yeah.
Yeah.
You can share, sir. You can share. Please share, sir.
Can you see it now?
Yeah, yes,
Yeah,
sir,
it's
it's
visible.
visible, sir.
Visible.
Okay.
Yes, sir,
Thank
it's visible.
Yeah. Okay. Thank you. So thank you, Priya, for the introduction, and I would like to say thank you to Professor Rajan, who helped me in systemizing the presentations. Actually, I'll be delivering 3 lectures. So the first lecture will be on fundamentals of aggregates. See, I'm working in IIT Madras from last 2 years. I'm working on different aspects of the payment materials. So me and Professor Rajan discussed, and then we came out that for the benefits of the students and other persons, what we can do, we'll be having 3 presentations, one on the fundamentals of aggregates, and then the next, that is at 11:30, we'll be having one lecture on use of innovative materials. That is mostly it will be aggregates, recycle aggregates, and in tomorrow's session we'll be having how to incorporate all these waste materials in cement concrete pavements. So you can see here it's a systematic thing, and I would like to say thank you to Professor Rajan, who helped me out in making this thing. So yeah, so we can start with the today's lecture. I know I'm late by 12 minutes, so I'll try to complete the things in the stipulated time. See, earlier, if you think like 10 years back, we were giving more importance on cement. Okay, whether it's a building concrete or the pavement, we were always worried about the cement, not about the aggregates, because we thought aggregates are inert in nature. It will not be reacting with anything. But because of the recent developments, now we get to know that it's not only the cement, it's also the aggregates which will be affecting the fresh state, hardened state, and durability properties of the concrete. That means we have to give the same respect to the aggregates that we are giving to cement. So this, if you can see here, that in buildings we are using 60 to 80% of volume by aggregates. In payments, it can be much more. In fact, it can be around 90% also, right? And earlier we were having, the aggregates around 50 paisa, 60 paisa. But nowadays, because of the ban on quarrying activities, you can see in Chennai also, okay, we are getting the aggregates from far quarries. Why? Because there is a ban on quarrying activities. We are not getting the coarse aggregate. And in fact, the fine aggregates, if I talk about, fine aggregates are very, very scarce now. So this increases the cost of the aggregates. So that's why we have to give the equal respect to the aggregates. Also, it will be affecting your yeah, now it's okay. Also, you see, like now it's monsoon in Chennai. Okay, when you are riding over the pavement, you are applying your brakes. It may lead to slipping or skidding, right? And mostly it is affected by the properties of the aggregates. Also, the abrasion resistance is affected by the properties of the aggregates. And durability, because we are surrounded by the sea. If the aggregates are not durable, definitely your concrete structure will not be durable. So that's why I say we have to give equal respect to the aggregates as we are giving to cement. So coming to the main part, that is fundamentals of aggregates. So my way of teaching is little bit different. I'll be giving the challenges and then we'll be thinking, okay, we'll be taking everything into practical aspect, not the theoretical aspect. So now the challenge, today's challenge is that I have to construct one pavement connecting, your JAIN college to IIT Madras. Okay, a cement concrete pavement, and we are thinking that it should last long for around 100 years. Means see, normally the design life of the pavement is 30 years, but we are planning to design, it's a hypothetical situation. We are planning to design for 100 years. So we cannot take any risk. Okay, and in Chennai, we have 5 crushing plants from which we can get the aggregates. And because see, in Chennai, we have the crushing plant, all will be crushing the same mountain, will be demolishing the same mountain and having the aggregates, right? So how to select a quarry from which we can get the good quality aggregates? Assume we have 5 quarrying plants in Chennai and one you can say in Cheyyar, okay, or Kanchipuram. So obviously we will not be taking the aggregates from Kanchipuram, right? Because transportation cost will be included and our payment should also be economical. So out of these 5 crushing plants, 1, 2, 3, 4, and 5, which one we need to select? So suppose Professor Rajan asks you, okay, guys, why don't you go to the crushing plant and characterize the aggregate and tell me which aggregate will be beneficial for our concrete? What will you do? Okay, so remember this picture in your mind and then you have to go along with my presentation. Okay, you have to be involved in the presentation. So the question is that which crusher I have to select so that my payment can stand for 100 years. So obviously you will be going to the site. Okay, and Professor Rajan will be calling you. Hey guys, what kind of aggregates is available there? What will you say? Okay, so before that we should know the classifications, fundamentals of classification. Normally we can classify the aggregates into natural aggregates and the artificial aggregates, which is a recent advancement. Earlier we know we have the igneous rock, we have the sedimentary rock, we can have the metamorphic rock. But in Chennai we are having the igneous rock, mostly granite. You see in the South India we are all most of the times we are having the granite aggregates. Okay, so you can call back and tell Professor Rajan that yeah, we are having the igneous rock. And nowadays we have the artificial aggregates, right? Manufactured aggregate, we can have the recycled concrete aggregates, recycled asphalt aggregates, whatever. There are different types of the aggregates. But then Professor Rajan will be asking you, okay, now you told me, okay, there is a granite aggregate. Which kind of the granite aggregate? Can you classify it? So as an engineer, how will you are classifying? We are classifying whether the coarse aggregate or fine aggregate. But it's not the only criteria. There are many criteria. So based upon the physical properties, we can divide. Like when the aggregates can be, split into two halves from one direction or both the directions, we can classify. And then we can do the some chemical characterization. We can say that it is the siliceous material. It is not made of clay. Or sometimes you can get the lime aggregate also, right? So we should know it. And obviously, as a civil engineer, we are always going with coarse aggregate or fine aggregate. But remember, you can see here, coarse aggregate can further be divided into three parts based upon the size, cobalt or boulders. Similarly, fine aggregates, we can have the fine aggregates. In fact, we can have the silt, we can have the clay, right? Similarly, based upon the shape, we can further classify the aggregates into round aggregates, angular aggregate, subangular aggregates, flake and elongated aggregates. And also based upon the surface properties, you can feel the aggregates. You can see even if it is polished, you can say it's a polished aggregate. Why we are reading about the classification? Because everything will be affecting the properties of the concrete. Let's say you are having a rough aggregate. Obviously, the bonding with the cement paste will be good. If you are having a polished aggregate, the bonding might not be good, right? But on the other hand, if you are getting a polished aggregate, the workability will be good, but not the properties. So what to do? How to decide? So before that, you should know the classification. And the last classification is based upon where you are using. For pavements, we are going with the normal weight concrete. Okay, the normal weight of the concrete is 24,000 kg per meter cube. Sorry, 2400. And if you are going for the big structures, heavy structures, you can get the heavy aggregates also. So in a nutshell, what I mean to say that there could be many classifications that you should know. Okay. Now the next question is that let's say you have decided 5 crushing plants. Okay, we saw it here, right? There are 5 crushing plants. Now your gang is going there. Okay, then you'll be going and collecting the aggregates for the characterization, right? So you might have did some test in your laboratory. What you are doing, you are taking 2 kg of the aggregate and then characterizing it, whether it's right or not. Because you can see here, there will be heap. Okay, large heaps will be there in crushing plants. Okay, and you are taking the aggregates from here. And then can you say that the entire properties can you visualize with the help of a small sample? No. If you are taking the aggregates from here, the other person will be saying this aggregate is good, but the person who is taking the aggregates from here, he will be saying no, the aggregates are not good. So there is a sampling technique, you should know it. Okay, so how to do the sampling? It depends upon the size of the aggregate. So normally we have 2 sizes. Remember this thing, I have met with many students and they are always confused. There are 2 sizes. One size is maximum size. Maximum size is, it is the smallest sieve through which 100% of the aggregate that will be passing. And remember, there is a difference between the maximum size when you are collecting it for the concrete pavement and for bituminous pavement. Okay, so I'll be considering everything on the concrete pavement. So it is the smallest sieve through which 100% of the aggregate will be passing. Let's say we have, 31 size aggregate, 25 mm, 19 mm. So you have to see from which size 100% of the aggregate will be passing. That will be maximum size. And nominal size is that largest sieve on which around 10% of the aggregates will be retaining. So based upon that, we'll be deciding the nominal maximum size. And based upon the nominal maximum size, we have to decide how much of the aggregates we have to bring to the laboratory in order to characterize it. Let's say 19 mm aggregates, nominal size is there. So you will be going to the crushing plant and you see a heap, 19 mm size is there. So what you have to do, you have to collect 25 kg of the aggregate. Remember, 25, it's not 2 kg, it's 25 kg. Now the next question is from where you will be collecting the aggregates. So you have to collect the aggregates from 10 different locations. Okay, so let's say this is the heap which is available. So what you have to do, you have to go with a board, cardboard. Okay, and then you have to divide it into 3 parts, top third, mid and bottom third. Then you have to place that cardboard inside the heap. Okay, so that the upper aggregates will not be falling at the below, right? So then collect the aggregates from here. Similarly, collect the aggregates from here. Remember, you have to collect in 10 different increments. And then you place your cardboard here and then collect from here, collect from here, collect from here, collect from here. How many? 6. Similarly, 7, 8, and on the back side, 9, 10, 11, 12, whatever. It should be minimum 10. And after that, what you have to do? You have to come to the lab. You have to spread the aggregates in a container. Okay. And then you divide it into four parts and then select any 2 diagonal. Remember, I'll again repeat, go to the site, collect 25 kg of aggregate when the nominal size is 19 mm from 10 different locations, from top, third, mid and bottom. Then come to the lab, mix all the aggregates together, spread it, and then divide into 4 quarters and select any 2 diagonal quarters. If it is a fine aggregate, then go with a PVC pipe. Okay, you insert it and get the fine aggregates from it, from different locations. Okay, and then you can come to the lab and you can characterize your material. Okay, characterization, you will be seeing, you will be well aware about the crushing value, impact value, so I will not be touching it. So the last characterization is that it's a recent one. In the last 10 years, it happened. Okay, so you can see here that the fraction passing 2 micrometer is clay, and we don't need clay for concrete. Although clay is used for cement manufacturing, but when you are using aggregates for cement production, it should not have clay. Okay, else it will be affecting the durability properties, right? And then nowadays we are having, you might have talked to some contractors. Okay, they'll be saying crushed aggregate, uncrushed aggregate. Okay, so uncrushed aggregate means the gravels that you are directly getting from the sea, or you can say rivers, big boulders, right? And you are not crushing it, directly using it. In that case, we are be calling them uncrushed. And if you're crushing it, then it will be called like crushed gravel. Or partially crushed means a blending between gravels, crushed gravel and the uncrushed gravel. As far as the fine aggregate is concerned, when you're crushing the coarser aggregates, there will be some dust. Okay, and that dust will be known as crushed stone sand or uncrushed stone sand. Okay, and if you're mixing it with natural sand, it will be named as mixed sand. Nowadays, we are calling it as M sand. So M sand is nothing but the dust from the aggregates mixed with the natural sand will be known as mixed sand or M sand. Now, what is happening when you went to the site? Okay, Professor Rajan is calling you and saying, what is the size of the aggregate? Okay, so normally it will be 20 mm, 40 mm, 63 mm, 16 mm, it can be there, right? But remember, there are 2 gradations. One is single size aggregates, and the other one is your graded aggregates. Let's take an example. Let's say it's 20 mm. What do you mean by 20 mm? How to know whether it is a single size or the graded? If you see the single size, that doesn't mean all the aggregates are retaining on 20 mm. This is a big confusion amongst the student, that 20 mm means everything will be retaining on 20 mm. No. If I take 20 mm, you can see it is passing from 40 mm completely, and it also passes from 20 mm from 85% to 100%. That means only around 15% is retaining, right? And then you can see on the 4.75 also it is passing around 0 to 5%. Okay, and if I take the graded 20 mm aggregates, you can see here it passes from 40 mm, it may passes 20 mm, it may passes 10 mm, and it may passes 4.75 mm. So what is the difference? The difference is that this 20 mm is having significant amount of the 10 mm aggregate also. You can see here it will be having significant amount of 4.75 mm aggregate also. Then why I am teaching this thing? Because in concrete we need graded aggregates. So if you are going to the site, you are finding 40 mm, 16 mm, 12, 20 mm, 12.5 mm separately, then you have to mix this aggregate in order to make a single graded aggregate size. Okay, so when you are going to the site, they are saying we are using 10 mm and 20 mm. That means it can be, most of the time it can be single size aggregate, and single size aggregate doesn't mean it is retaining on 10 mm. It will be passing through 10 mm also. Okay, as far as the fine aggregates are concerned, in the market, if you go to the market or the crushing plants, you'll be seeing there are different zones: zone 2, zone 3, zone 4, zone 1 fine aggregates. Okay, and as for IS 383 specifications, you can classify which variety of the sand is available. But remember one thing here. See, in these respective codes, you will be seeing different kinds of the fine aggregates, right? And when you are going to the site, there will be deviation. Not all the fine aggregates that you will be getting will be having its limits between specified limits. There will be marginal deviation. In that case, what to do? So the code, that is IS 383, it allows, okay, IS 383, we have recently revised it. Okay, it allows you to do little bit things. Okay, but deviation should not be there in 600 micrometer sieve. So if you find any fine aggregate and then you see that there is a 5% deviation in other sieves, you can go through it. You can say, yeah, this is a zone 1. But if it is deviating the 600 micrometer sieve, then you have to reject that sand. Okay, remember this thing. Why? We'll be discussing in the later slides. So we have different characterization thing. You might have seen in your college also now, because of the pandemic situation, everything is closed. But I assume that most of the students, did the transportation laboratory. So we have to characterize the aggregate for specific gravity, density, toughness, strength, abrasion resistance, polishing value, elongation and flakiness value, and the durability aspects. And based upon all these properties, then you have to decide which crushing plant you have to select. The aggregate whose specific gravity is good, whose water absorption is lesser, whose density is more, whose toughness is more, strength is more, hardness will be more, then you can say, yes, out of these 5 crushing plants, I'll be selecting this crushing plant. Okay, and then you can come to your professor and say, sir, out of these 5 crushing plants, we are selecting this crushing plant because the properties are good. Okay, what properties? What we have discussed. And then remember, for payment application, we have given different specifications. Okay, you can go through IS 2386 guidelines, and you can see whenever you want to use for building or payment application, the water absorption of the aggregate should be less than 2%, impact value should be less than 30%, crushing value should be less than 30%, abrasion should be 30%. Okay, so based upon these properties, whatever the crusher, let's say what happened, 2 of the crushers were giving good properties. Now, which crusher you need to select? Then it will be depending upon the economy, how far it is from our site. And in today's example, our site is connecting JAIN college to IIT Madras. Okay, whichever crusher plant is very near, we have to select that. Then now you will be discussing, see, my mountain is same, from same mountain, okay, they are crushing the aggregates, giving me 20 mm and 10 mm. This crusher plant also, and similarly this crusher plant also is using the same mountain for producing 20 mm and 10 mm. So why the aggregate properties are changing? You must be thinking it, right? Yes, because the aggregate production is having a significant effect. Normally what happens, you will go to the mountain, you will demolish the mountain, right? You will be getting big boulders. So then you will be bringing that big boulders, or maybe you are crushing the big boulders at the site also, you are crushing it. Okay, and then you will bring it to the your crushing plant, and you will be again crushing it. So you can have various crushing mechanisms: primary crushing, secondary crushing, tertiary crushing, or quaternary crushing, in which you are reducing the size. So let's say this was of 100 mm. You keep on crushing it, and you got a aggregate of 4.75 mm. Okay, so now do you think that the crushing thing will be having an effect on the properties of the concrete? So normally we are having 3 mechanisms. We'll be crushing first, then again crushing it, and again crushing it. And the crushes that you are using will be having some effect. So in the site, we have different crushes. We have a jaw crusher, okay, we have a cone crusher, we can have an impact crusher. So all these crushers, okay, we are using in order to produce aggregates. And there is a significant effect also. Earlier we were not thinking, we were thinking, okay, we are just crushing the aggregates, right? But now the mechanism, the principle that you are applying to crush the aggregates will be having an effect, significant effect on the properties of the aggregates. We have many studies, and what we found that by changing the sequence means, let's say you are having first jaw crusher, then impact crusher, then cone crusher, or you can have first jaw crusher, cone crusher, and impact crusher. Impact crusher can be of different varieties. By changing the mechanisms, you can get the aggregate properties different, which will be beneficial. So as a researcher, what you have to do, you have to crush the aggregate with different mechanisms and see which aggregate is giving you good properties. Okay, so if you want to do some research, if you want to do your master's or the PhD, or in fact, if you want to do a good BTech project also, okay, you can definitely take this one. You can go to the crushing plants, see what are the mechanisms they are using it, document it, bring the aggregates, do the characterization, make concrete, okay, find the strength, and then you can see there will be a difference. Okay, so it's there. Now the next question is that you must be thinking, for buildings, you're always using 20 mm and 10 mm aggregates, right? And for the pavements, you are using 31.5 mm size aggregate. Why there is a difference? Okay, the difference is that in our payments we are having different layers. We have the wearing course, we have the base course, we have this drainage layer we can call as a granular sub-base course, and we have the subgrade. Okay, so how to decide what should be the size of the aggregate? So you know the formula, stress is equal to load upon area, right? Which shows that if you increases the area, the stresses will be reducing, right? So how to increase the area? Let's take an example. Let's say you are taking one aggregate of 150 mm size, applying the load. So you can see here the area of load application is this, and the same area is there. Okay, so the stresses which is occurring at the top, the stresses at the bottom will also be same. Okay, and we know in subgrade what we are using, soil, mostly soil, and it is the weakest link in a payment system. You have to protect the subgrade. So in the next step, what we can do, we can divide, we can crush this aggregate into 3 aggregates. Now what will happen if you apply the loading at this area, but the load distribution will be there from a bigger area? That means the stresses will be reducing. Similarly, if you further crush this aggregate into small pieces, so what will happen? The area will further increase, and if the area is increasing, the stresses on the subgrade, which is the weakest link, is reducing. Okay, so nutshell, as a thumb rule, what you can do, how to decide the aggregate size. The aggregate size, you know your subgrade will be around 500 mm. Okay, so 500 divided by 3 or divided by 5, this should be your aggregate size for aggregate to aggregate transfer. In case of the concrete, generally there is a mixed feeling. There are 2 schools. Okay, one says that if you have a bigger aggregate, and so the surface area will be lesser, and if you crush the aggregate into 3 pieces, the surface area will be higher. If the surface area is higher, you will be needing more cement, and you know cement is the most expensive portion. Okay, so why my thing is that I have to construct one payment that will be lasting long for 100 years, but it should be economical also. So what I'm doing, I'll be using a bigger size aggregate so that the surface area will be lesser, and if the surface areas will be lesser, if I make the payment, okay, I'll be needing lesser cement to bind the aggregates and economical. Okay, however, there is other school also, different school also. It says that if you have large size, then mixing will be a problem. If you have the large size, then your properties will be lesser because aggregate to aggregate interlocking will not be there, right? So therefore, we say that if you want to make a very, very good concrete, don't increase the size beyond 19 mm. If you're going with the normal concrete, then in case what you can do, you can use the same formula. The maximum size of the aggregate should be 1/5 of the total thickness of the pavement. So if let's say if your slab is 300 mm divided by 5, okay, you will be getting 60. So the size of the aggregate, it should not be more than 60. Okay, so you can get the strength as well as you can get the good mixing also. Okay, so now the question is that why we have to mix 2 aggregates together. If you remember from slide number 5 or 4, we told that when you are going to the crusher plant, you will be getting different heaps. 20 mm heap will be there, aggregate heap, 16 mm heap will be there, 12.5 mm heap will be there. Okay, and we have to club everything together to make a graded aggregate, right? Similarly, if I talk about the concrete payments, you know we have different layers. We have the embankment, we'll be having subgrade, we'll be having GSB, we'll be having DLC, we'll be having the slab. Okay, and if you read the specification, Indian Road Congress specification, it says that the aggregates that we are using should be a combination of 26.5 mm. It should also have 4.75. It should also have 300 mm. It should also have 75 micrometer. Okay, so remember there are 2 reasons. One, you have to mix different coarse aggregate together to make a graded aggregate, and then you have to mix fine aggregates together along with the coarse aggregate in order to make the specification, the gradation, which will be falling within stipulated limits of MORTH or Indian Road Congress. Okay, for different layers, we have different gradations, right? Then because why? Then the question is why we have to grade the aggregates, right? So let's take an example. What you do, you take 26.5 mm aggregate. It's an example. You can take any size and fill in a container. Okay, completely packed it. And then you pour some water. Okay, you'll be seeing that, let's say 100 ml of water was required to fill these voids. Okay, and then what you do, you add 9.5 mm aggregate in this mixture. So what will happen? The 9.5 mm aggregate will be smaller in the size, right? So it will be filling the voids. So if the voids are filled by the smaller size aggregate, you will be needing lesser quantity of the water to fill those voids. Then do one more thing. You add 4.75 mm aggregate in it. Okay, let's say these are the 4.75. So big size aggregates were there. They were having some voids. Those voids were filled by smaller size aggregate. And then smaller size aggregate will also be having some voids. Those will be filled by 4.75 mm aggregate. And thus you need significantly lesser amount of the water to fill these voids. Okay, one second, some noise is coming. Yeah, sorry for the interruption. So what we need see that if the amount of the voids are lesser, that means lesser cement is required. And if the lesser cement is required, your concrete will be better and economical. So generally what we have seen that if you have coarse aggregate and fine aggregate, if you are mixing in a proportions of 60 and 40%, your voids will be least. Okay, you can take as a thumb rule, but it's not always the same. When you go and ask an engineer, they will be saying 60 and 40. 60% coarse aggregate and 40% fine aggregate. It's not always same. Okay, it can be 35%, 65%, it can be 50-50 also. So you have to find it, how much should be the proportion so that our voids will be the minimum, right? So, yeah. So, now, right. So why, when we are mixing the aggregates, we can have different gradations. Okay, I hope you can hear me, right? Professor Razan, can you hear me?
Sir, we can hear you.
Yeah, thank you. So,
Sir, very much audible. Please continue.
okay, thank you very much. So when we are mixing the aggregates, okay, so you can see here we have different gradations. We can have a well-graded aggregates, we can have the poorly graded aggregates, we can have the gap-graded aggregates. Okay, and what we need always well-graded aggregates. Remember, okay, because if you are having the well-graded aggregates, you can see there will be lesser voids and the cement requirement will be lesser. Let's take an example. Okay, Professor Rajan sent you to the site, and you can see here you'll be getting different heaps. Okay, this is the picture that I took from a crushing plant in Chennai. We can see here there will be 20 mm aggregate, it will be 10 mm aggregate, there will be 40 mm aggregate, there will be filler material. And how to mix all these aggregate together? This is the question, right? So let's say we have three aggregates, 20 mm aggregates, 10 mm aggregates, and some fine aggregates. How to mix them together? So what you have to do, you have to open your IRC specification, Indian Roads Congress specification, and they will be saying that this limits is this thing. That limits means from 75 micrometer sieve, 5 to 10% of the material should be passing. Okay. Then how to mix these aggregates to fall within the limits? This is the question. So we have different methods. Okay, I'll be teaching you all the methods so that maybe I know you are civil engineer. Okay, you will be going to the site, and then there will be different questions. Your boss will be asking you, blend these aggregate together. Then you'll be thinking how to blend the aggregate. Simple thing is there, hit and trial method. Let's say this is the specification. Okay, let's say I'm taking only one seed, 4.75. Okay, so 4.75, you see here material A 6% is passing, material B 100% is passing, material C again 100% is passing. Okay, and your specification says that when you are mixing three aggregates together, 40 to 50%, 55% of the aggregate should be passing. Then how to do it? So we can go with a hit and trial method. So let's say specification says that from 4.75 mm sieve, 40 to 55% should be passing. We can take the mid value, let's say 50. 50% should be passing. And you have three materials, A, B, C material. Okay, so what you have to do, you have to multiply A by some proportion, B by some proportion, and C by some proportion. Let's say 0.3, 0.3, and 0.1. So in total, how much? You can say 0.4. So 4, 5, 6, 7, 8, 9, 10. Okay. That means 30% you are taking A material, 30% you are taking B material, and 40% you are taking the C material. And when you are combining all this material together, then you will be getting 50%. Then you will be thinking how this person came out with these values, because there is a principle behind it. What we can do, let's say we take two materials, only A and B material, and you have to mix A material some proportion, you have to mix some proportion of B material in order to get the specification. So what we can say, A plus B should be equal to 100%, 1. Then A is equal to 1 minus B. So we came out with these formulas, that we have to mix the B material in this proportion, we have to mix A material in this proportion. Okay, let's take an example. This was the material passing from A and material B. Okay, and this is the specifications. Okay, these are the specifications. We took the mid value. Now the first step will be, because see, it's a hit and trial method, trial and error method. You can have your Excel program, because always we have to change the values. Okay, but let's say you are standing at the site and you don't have the calculator, you don't have the Excel program, you don't have your laptop, you don't have the phone. How to do it? The first step will be, you have to see the critical sieve. Critical sieve means that sieve that can divide into aggregate into two parts, coarse aggregate and fine aggregate. Okay, normally coarse aggregate are the aggregates which are more than 4.75, and fine aggregate are the aggregates which are less than 4.75, right? But in my material, what you can see, that from 4.75, 16 mm is 16% is passing. We cannot say 4.75 is the deciding sieve. But if you see here 2.36 sieve, over which 100% most of the aggregates are retaining. Okay, and if you see material B, almost more than 80% is passing from 2.36. You can say 2.36 is my critical sieve. Okay, so 2.36 is your critical sieve. Then the formula is B is equal to P minus A upon B minus A. Okay, so what is P? P is your specifications. Okay, so specifications say P is equal to 42.5. A is material A. What is material A? 3.2. Then B is material B. Material B value is here 82. So if you keep these values, you will be getting B is equal to 0.5. And A plus B is equal to 1. So A will be 1 minus 0.5 is equal to 0.5. Now the next step is to check whether, if I am taking 50% of B and 50% of A, whether I am getting the gradation within the specification limit. You just multiply everything by 50, this also 50, and C. So I am multiplying by 50. See, material A 50%, material B 50%. Okay, you have to multiply all the values by 50 and then add both the things together. Okay, and see whether the limit says 80 to 100 minus 95. Yes, it is falling under. The limit says 50 to 70, my value is 56. Yes, it is right. My limit says that 80 to 29, it is 25.6, it is between. My limit says 4 to 10, it is 4.5. That means okay. So that means the proportion that you have decided is well enough. Okay, and if you have, let's say, 3 aggregates, what you can do, you can use the same formula. Okay, you have to first decide the critical sieve, but working with the 3 formulas is always little bit tricky. So I'll be asking you, why don't you go to your computer, you make an Excel program, and that Excel you can do it. It's a very simple thing. But if you don't have the Excel program, you can go with the triangulation chart method. Okay, triangulation chart method is generally used for three sieves. Okay, when you have 3 aggregates, aggregate A, aggregate B, and aggregate C. Okay, and it is the one of the best method. And every aggregate we can divide into 3 parts. Okay, let's say this is my triangle. Okay, you have to construct one triangle. It should be an equilateral triangle. Every material will be having 3 things. One, coarse aggregate. Coarse aggregate means up to 4.75. It will be having fine aggregate. Fine aggregate means 4.75 to 75 micrometer, and C less than 75 micrometer. So every aggregate you have to divide into 3 components. More than 4.75 will be calling as a coarse aggregate. 4.75 to 75 micrometer will be calling as the fine aggregate, and less than 75 micrometer that will be calling as filler material. Okay, so we'll take A. Okay, so in A, how much is the 4.75? So remember, this is percentage passing. So how much is retaining of 4.75? What you have to do? You have to simply subtract it by 100. Okay, so material A, how much is more than 4.75? It shows 19%. 19% passes. So how much will be retaining? 100 minus 19 will be 81. Okay, then how much is between 4.75 to 75 micrometer? Okay, so what you have to do, 19% is passing, okay, from 4.75, and 2% is passing through 75 micrometer. So how much is being retained? 19 minus 2, 17. 17%. This material is giving 17% of fine aggregates. And how much it is giving filler? 2%. Similarly, take B material. How much quantity is the coarse aggregate? 0, because there is no material retaining on 4.75, 100% is passing. How much is the fine aggregate? Fine aggregate is 4.75 to 75. You see, 3% is passing, that is 97%. Okay, see, in 1 hour we have to finish most of the thing, but yeah, I'm trying to finish most of the things so that when you go to your house, okay, when you read it, I'm writing everything so that it will be beneficial to you. I'll be sharing this presentation with Professor Rajan. Okay, so similarly, you have to do for C material also. Okay, and then similarly for specifications also. For specifications also, you have to see how much coarse aggregate will require. 100 minus 48, 52. How much fine aggregates it is saying? So 48 minus 8, you will be getting 40%. And how much filler material should be required? So 100 minus 8% is passing, so that means 8% filler material it is giving. Then you have to construct one triangle. You have to construct your points, A point, B point, and C point, and then you have to use this formula, and you can get the proportion of different materials that you have to use it. Okay, simply what we are doing, we have to blend 3 aggregates together so as to meet the specifications. How much quantity need to be mixed, we are finding it out. There is one more method. It is very, very famous method. If you know the Pradhan Mantri Gram Sadak Yojana, right? So Professor Praveen Kumar is there, okay, on whose model which we are mostly following for Pradhan Mantri Gram Sadak Yojana. So he was my supervisor, and then he was always using this method. He called as a Rachford method. This method is one of the best method, he says, when you have to mix any quantity of the aggregate. What you have to do, you have the blending curves. Okay, material A, material B, material C. You just draw the curves. Here you see size, here percentage passing. After that, you make it straight. Okay, because see, the curve is like this, right? You make it straight. How to make straight? Draw one line. How to draw the one line? Because somebody will be drawing this line, somebody might draw this line. So when you are drawing this line, you have to see the area on both the sides. Okay, this area on this side and this area should be minimum. When you have the minimum straight line, that line will be better. Similarly, draw one straight line for material B, draw one straight line for material C. Okay, and then you have your this is your specification line. Okay, specification line. So then what you have to do, when you're drawing this line, you take the lower end, connect it to the upper end of material B. Similarly, lower end of material B, connect it to upper end of material C. So obviously it will be passing your specification limits, or we can say diagonal line. Okay, then what you have to do, you have to draw one more line, and then you can say this is your material A, this is your material B, and this is your material C. Again, I'll repeat. What you have to do, you have to draw your curves, draw one diagonal line connecting 0 to 100%, and then you make it straight. Okay, you make it straight. It's a very simple formula. And then you have to connect these lines again, bottom to top. And then wherever it is crossing the diagonal line, you have to again draw some more lines connecting on the percentage passing, and then this proportion will be A, this proportion will be B, and this proportion will be C. It's a simple formula. Okay, you can do it. Now the question that will be coming, that this professor is saying specification, specification, specification. From where we are getting all this specification? I am saying IRC, Indian Road Congress, or Ministry of Road Transport and Highways, that is MORTH. Okay, but how to decide? And nowadays, we know we don't have the aggregates. We have to use some recycle aggregate that we'll be discussing at 11:30. How to decide we can use the recycle aggregate. Okay, from where I should get the specification limits for recycle aggregate. Okay, and how to ensure that if I'm keeping my aggregate gradation within the specification limit, whether it will be giving me good results in the site or not. How to decide? For that we have some formulas. Okay, so normally what is happening, we are using Fuller and Thompson model. Okay, the simplest model is there. What is percentage passing is equal to 100 into bracket D upon D max. D max is your nominal size of the aggregate and D is your size of the aggregate. Ki power N. N is your shape factor. You can keep it as 0.45 and then keep on doing. Let's say, let's take an example. You went to the site, crusher plant, you found different aggregate, 19 mm aggregate, 12.5 mm aggregate, 9 mm aggregate, 75 micrometer. Then you have to see, okay, how much proportion, if I mix all these aggregate together, then I'll be getting a really well graded aggregates. Use this formula. How to use? First decide what is D max, that is maximum size. Maximum size is 19 mm, right? Okay, put 19 mm here. What is D? D is in 19, again 19 mm. So 19 divided by 19 ki power 0.45. You will be getting your results. Similarly for 12.5, you just simply put here 12.5 and use the same formula, you will be getting the values. You can see here. So this shows that if you use this formula, you will be getting the recommendation limits. Okay, and if you are using this formula, I'll be guaranteeing you that you will be getting a relatively well graded aggregate gradation. Okay, now the question is that we need two things from our concrete. Okay, one is workability and the other one is strength. Okay, now you're the student of civil engineering, you know the workability. Workability means how much it is flowing, right? You'll be saying, but no, it's not like that. Workability means how well we can play with our concrete. Okay, for buildings you need more flowable concrete. For pavements we don't need more flowable concrete, right? We need a thixotropy. Thixotropy means it's a property. When you are placing your concrete, it can stand. Okay, it should not be flowing, it should be standing. But when you are vibrating it, it should flow. Okay, it should flow. And again, when you are removing the forces, it should again stand. That kind of the property will be requiring for concrete pavement. Remember, if somebody is asking you, the concrete that you are using for the buildings and the concrete you are using for the pavements are same or not, you should say no. Because in buildings, we need workability. In pavements, we need a property named as thixotropy. Thixotropy means when you are placing your concrete, it should be there. When you are vibrating it, it should flow. But again, if you are removing the forces, it should again stand. Because in concrete pavements, we are removing the formwork just after placing. We are not waiting for 24 hours if you are going with slip form pavement. So how to make that material? That material, we have to play with the aggregates only. Okay, you have to play with the aggregates only. Sorry. Okay. I hope you can still see my screen. I did some settings. Yeah. Okay. So in my pavement, the fine aggregates plays a very important role. Fine aggregate, you will be saying 4.75. No. We have two fine aggregate, coarse fine aggregate and fine aggregate. Fine aggregate means from 2. If it is 4.75 to 2.36, and we can have from 2.36 to 75 micrometer. These are the two sizes of the fine aggregate. This is coarse fine, this is fine. Okay, so the finer aggregates will play an important role in achieving the thixotropy. Okay, it should be having significant amount, not the more amount, not the less amount. Okay, so now the question is that, let's say you are sitting in the laboratory. Obviously, you'll not be going to the field, right? How to ensure that the aggregates that you are blending together will be giving you good workability, good strength at the field? How to do it? Now, it's a pandemic situation. We have to construct one pavement that should stand for 100 years, right? Without doing the laboratory trials, without doing the field trial, how to ensure it? We have some models. Okay, so maybe what you can do, I'll be sharing my presentation. You can just go through the presentations. Okay, but yeah, briefly I'll be explaining you. We have one model. We named this model as 8 to 18%. Means you should ensure that your aggregates between 25 mm to 6 600 micrometer should having at least 8% of the fraction and maximum of 18%, because if you are having more aggregates, then workability will be issue. If you are having lower aggregates, then you will not be giving strength, right? So you have to draw one chart. You have to draw two lines, 18 mm, 18% line and 8% line, whatever specification, and then you have to plot your curve, and this curve should be in between this thing. We have another thing which recently got very famous. Actually, in Texas, in US, they made 500 different mixtures with different gradation, different sources. Okay, and then they constructed different payments, and then they saw that what should be the gradation, and they found that the percentage between 2.36 to 600 micrometer should be greater than 15%, and fine sand, that is from 2.36, it says that it should be between 24% to 34%. 24% to 34% should be between 600 micrometer to 75 micrometer. If you are making sure that whatever aggregate blending you are doing, if between 2.36 to 600 micrometer, if you are having 15% of aggregate, and between 600 micrometer to 75 micrometer, if you are in 24 to 34%, that means your concrete will be good. It will be giving you good properties. Okay, and now you can check it. Okay, so I wrote it. What you can do, you can go to your home. Okay, obviously you are at your home, sorry, and then you can see, okay, you can mix different aggregates together and see whether it is falling within this curve or not. If it is falling within this curve, you can sit, relax. You can say at the side, if you're following my gradation, you'll be getting good workability. So recently we have updated one thing. We came out with a coarseness factor chart. Okay, which says that it's not only the workability. Okay, when I mix, see, when you're taking the aggregates together, right, we'll be mixing the cement also in it. And cement is one of the influential factor which will be affecting your workability and strength. So why should not we include the cement? This is the question. Okay, so we came out with some models, coarseness factor and workability factor, which says that the gradation that you are using, okay, can be divided into two parts, 9.5 and 2.36. And the cement that we'll be using, keep your cement here, you get these factors, and then you plot in this coarseness factor chart. The gradation and the quantity of the cement, when you combine both the things, your value, that is relation between workability factor and the coarseness factor, should be as close to as 2 Joule. If it is there, then they are guaranteeing you that your payment will be performing very, very good. So in a nutshell, what I can say in today's presentation, what we discussed, that how to mix the aggregates together. Okay, normally what we are doing, we are not giving the respect on mixing, but you have to give. And how to make sure that without doing the laboratory trials, without going to the site, how we can mix the aggregates together so that our concrete payment that we are casting, that we are producing, will be good enough. So this is my, what you can do, you can go to the house, you can check the gradations given by IRC 58, okay, or whatever the IRCs, whether it is giving you the good properties or not. Without constructing the payment, you can check with the help of these formulas. So this was my last slide. Now I'll be open for the questions. If you have any questions, you can type in the chat box.
Thank you, sir. That was really very informative session, sir.
Yeah, thank you, Priya.
Participants, if you have any queries, you can ask us, sir. You can unmute your mic and you can also ask the questions. Or you can give your questions in the chat box.
I know it was a big session. I was late by about 10 minutes, so that's why. See, remember this thing. In this session, we have discussed how to mix the aggregates together, coarse aggregate and fine aggregate. Okay. So we discuss about various methods, how to classify. See, you will be going to the site, then you will be having this question, which crusher plant you have to decide. Okay, so how to select the crusher plant? You can use this method that I just spoke to you, okay, in order to characterize the material, and then in order to decide which crushing plant you have to decide. Okay. Yeah. If you have any questions, please unmute yourself, or you can write in the chat box. Okay, we'll be taking your questions. Any type of questions. Anyone?
Participants, if you have any queries, you can ask us, sir.
Yeah, Milind Rotaj Gupta. He wanted to ask why only 20 mm, 10 mm aggregates are used. See, for building concrete, we are using 20 mm aggregate because high strength concrete. As we discussed, if your size is increasing, okay, then the workability characteristics will be reducing. Okay, and there is one more parameter known as interfacial transition zone. Okay, if you want to get good strength, use lesser size of the aggregate, because if you are using lesser size of the aggregate, then the bleeding water will be lesser, and if the bleeding water will be lesser, water by cement ratio will be lesser, and you will be getting good strength. That is the reason we are restricting below 20 mm. But for pavements, it's different. For pavements, we discussed it should be the total thickness of the pavement, thickness of the slab, divide by 3 to 5. You do divide by 5, that should be the maximum size of the aggregate. Normally for PQC, that is the bearing slab, we are using 31.5 mm aggregate. Okay, because we need aggregate to aggregate interlocking. That's why we are restricting it as 31.5 for PQC, 26.5 for base coat, that is dry-land concrete.
Thank you, sir.
Hello.
Yeah, Ranganath. Yeah.
So in most specification for WMM, there are for GSB there are 5 gradations are there. Why it has divided like that, sir?
5 gradations for
GSB.
GSB. See, GSB, we have 5 gradations, right? The thing that is required from the GSB is drainage. Okay, so for drainage, we have actually 2 GSB layers. Okay, so one is as a separation layer, one as a drainage layer. Okay, so for separation layer, they want that it should separate your subgrade from the top layer. So the gradation should be very, very dense graded. Okay, that's why we have gradations. For drainage, we need gap gradation so that the water can easily flow it. It should have good permeability characteristics. For that, we have provided 3 gradations. What I've seen normally when you're going at the site, it's not always possible to get the exact gradation that is available. Okay, so based upon that, we have given you 5 gradation. 2 when you are using for GSB as a separation layer. 3 as it when you are using the GSB as a drainage layer.
Thank you, sir.
Thank you.
Sir, we can have a 10 minutes break and shall we start our next session, sir?
Yeah, sure. Yeah.
Participants, we will be giving a 10 minutes break and the next session will be started by 11:15. I request you to join the session by 11:15. Thank you, sir.
Thank you, Priya.